We are Aditya and Nikhil from Team BIOS, and we work in binary exploitation. And today we are here to give you a brief introduction to binary exploitation. And this is day one.
So on the first day, we're going to discuss what is exploitation, why are we doing exploitation, what is a okay, sorry. So why are we doing exploitation? The stack registers the assembly, that the stuff that you learned yesterday. So yeah. So what is exploitation? As we know, nobody is perfect in this world. We all make mistakes. Like I don't know. We all make mistakes, even in the simplest things that we are supposed to do. Programmers are no different. Even while writing the simplest of codes, we make mistakes. So sometimes these mistakes can be taken advantage of. These mistakes also can act as a security flaw or a security threat to the program. That is a vulnerability. So attackers tend to look out for these vulnerabilities that we make, that any programmer, any human makes, and they try to take advantage of it. And they, using that security flaw or the vulnerability, they try to get the control of the target computer on which the flawed program is running on. So basically, even a simple problem, a simple mistake in a program in your computer, it can happen to you, it can happen to me, it can happen to anyone in your computer, can make the system vulnerable to attackers. So the attacker, in this case, which is going to be you, will be giving a set of inputs to the flawed program, to the flawed program, in such a way that it will influence the flaw which is going to be found by you itself, and you can take advantage of the program, get the control of the whole system of the target computer. So this is more or less exploitation, getting control of the target computer. So okay. Next.
So we now understood what is exploitation as such. But like, why do we do it? Why do we want to exploit someone else's system? What do we gain from it? So as Nikhil said, in all the programs that generally we write, there are chances that there is some sort of error done by the programmer. So what binary exploitation basically does is that we take that particular mistake that we now would call as bug and exploit it. So it can be used to compromise the integrity of the program and also sometimes the target system as well. So one of the major factors we can learn from doing exploitation is that how much would we think that a system is secure? If we are able to find vulnerabilities and bugs, we could compromise the system. So what we're doing and why we need to exploit systems is because we could just find that the backdoor and make sure that that backdoor no longer exists and make the system more secure. So that's one of the major reasons why we do binary exploitation as such. And in terms of CTFs, we just do it just for the flags. So one of the prerequisites for the introduction to binary exploitation session that we are having today is the day one and day two of the introduction to reverse engineering, which happened in the last 2 days of the InCTF trainings. So in case you've missed the 2 days of trainings, you should at least have a basic understanding of x86 or assembly language, and also how the stack works and also the binary. So in case you have no clue about the two things that I said, we will be running through these topics in a brief way. So stick ahead.
Don't worry. So in today's session, we are going to learn what binary exploitation. So we're going to learn what is a binary first. Okay. So what's a binary? How a compiler compiles a program. You'll know what a compiler is. You'll know about the different architectures of binaries, which is going to be available to us as challenges as such. We'll know about executables, assembly code, the endedness in memory, the stack. We'll know about the stack. We'll revise it. what is the stack, the registers, the function prologue and the epilogue, the calling convention, 32-bit and 64-bit and all. And we'll just brief through with the most simple binary exploitation challenge, which is a buffer overflow. Okay. So, yeah. What is a binary? So a C code, a CPP code, a Java code, etc., any languages code, which is converted into a format that only the computers can understand, is called a binary. So programming starts with having a clever idea, writing code in programming language of your choice. For example, C, like my favorite is Java. After that, compiling the code into a binary will help with the help of compilers like GCC, which can execute, after which you can make them execute to get your desired results. So the binary file above mentioned, follow the specific structure. It will have an ELF thing. ELF means executable and linkable format. So these files, the executable and the linkable format, are specific to the Linux operating system. So we'll know how a compiler compiles a program. So we have a source code, which is a high-level programming language. It can't be understood by the computers. Okay, computer only understands, the CPU only understands ones and zeros. So the compiler takes the source code, turns it into an object file, converts the source code into a machine language module called an object file. Then the object file, another specialized program called the linker, combines with this object file with other previously combined object files in a particular runtime module to create an executable file. This executable file is what I'm talking about, is the ELF in Linux. It will be an exe in Windows, ELF in Linux. Okay, so next. So now you have written your favorite Java code, C code, or CPP code. So how would you compile a C program and make it convert it into a binary? So first you're gonna have GCC installed in your system. So with this command, run this command on your terminal, you'll have GCC installed in the system. After that, GCC hello.c. Now hello.c is the name of the program that you're gonna type. Void main, that everything, print hello world and all. This is the hello.c program file. Now hello is gonna get created on the directory on which you're gonna run this command. So hello is gonna be name of the binary file that you're gonna create. Okay. So after creating the binary file, you would like to run it, obviously. So before running it, you're gonna give the binary file some permissions to run, right? So that permissions are given by the command chmod plus x / binary or simple chmod plus x binary. Okay. After which you are able to run your binary file, which you have made on the last slide. And after that, actually running the binary will come with / binary. Simply means that you're running your binary file, executing it, running it. But you get a binary file in a CTF challenge, but you don't know about what is it, what kind of architecture is it made of, what linker does it uses. So for that specifications of a binary file will be provided to you by this command, file binary. Okay, when you get file binary, you will get everything. It's a 64-bit, it's a Linux or MIPS or ARMS, or it's everything. So we'll talk about the different architectures in of binaries that are available. It's Intel, which has two things, 64-bit and 32-bit. 32-bit and 64-bit are slight different from each other. We'll be discussing about it. And the other two are MIPS and ARMS, and there are various of other architectures that are there on the computer world, and you will get to know if you'll dive deep into exploitation. So yeah, in this training we'll be using 32-bit and 64-bit as examples of binary exploitation challenges to you all, and we'll explain you explain it to you in a very detailed way. And MIPS and ARMS, I hope that you can do it on yourself. So executables.
So as Nicola said, we have run through what a binary is. So binary and executable are the same thing. So defining it once again, it is a machine code for a computer to execute. So executables can be divided almost three ways. ELF for the Linux-based systems, .exe for the Windows-based systems, and also Mac format for the Mac OS. So how to run, we already know, / your executable name. So next coming through is the basic assembly language as such. So assembly language, one of the major questions that comes even before your understanding what assembly language is. Why would we want to learn a language, assembly language, when we have something so easier and more understandable like the higher level languages like C, C++, Java, etc. Machine doesn't understand all the programs that we write in the form it is, in the human readable form. It just understands zeros and ones. So we possibly can't understand the huge amount of zeros and ones that the machines can understand per se. So the linking between the high level languages and the bytes that the machines can understand is assembly language. So it's basically the zeros and ones, but in a more text format or the readable format that humans can generally understand. This is the closest that we can go to a machine code per se. So programs written in assembly language are compiled generally by an assembler. Every assembler has its own language, which is designed for one specific computer architecture. So in this, we have given two sections. One is the C code, and another is in the assembly code. So I'm just briefing over this because this was already taken in the reversing session. So first of all, in C, we have hash include std.io.h. So what it does is that it's basically a library where we could call upon different functions. So in this, we're using printf. So printf is being called in this particular program. In the same side, if you look at the assembly, you could see that extern printf is being used. So extern we're using so that we could just call that particular function from the library, and it is not per se defined in that particular program that we have written. So next we have a main functions being defined, and similarly in the ASM we could also see a global main being defined as such. So and main colon is basically the entire main function which is inside the parenthesis in C being defined in the ASM. So inside it, we could see that just specifically going through this portion, printf hello x86 assembly. So if you go through here, we have a push message and call printf. So here we could see that the message is right now present in the section .data. So that is where we are storing the string that we are going to print. And that is being done in the .data section. And then afterwards, we are calling the function called printf. So we are passing the argument and we are calling the function printf. So this is basically exactly kind of similar to what is there in the C. So the extra thing which is there is this weird looking things, which is push EBP, move EBP ESP, move ESP EBP, pop EBP ret. So what exactly this does is that it creates a stack. So whenever you run or execute a particular program and when the function is being called, at that point of time, a stack is being created for that particular function. So imagine for the time being stack as a book, a pile of book. So right now, once the main function is being called, the first thing that we do is to create a stack for it. So to create a stack, if you've been to the reversing session, we would just understand more better that we're just doing push EBP, move EBP ESP. So EBP is the base pointer of the stack. So imagine a book is there. So you're first of all keeping a book on the table, okay? The first book is being called as EBP, and then you have this book which you would want to keep on top of the stack. Like whatever, how many ever books you're going to keep on the table, this particular book should always be on the top of the stack. So imagine that as ESP. So you have one book that is dedicated to the bottom of the stack or bottom of the pile of books, that is EBP. And there's another book, ESP, which is always dedicated to the top of the book pile. So right now when we do this, we are basically creating a stack frame. So in order to collapse the stack frame, what we do is that we take the book, which we always keep at the bottom, to the top of the to the book that we always keep at the top. So imagine we kept this first book EVP, and then we kept another book ESP on top of EVP. And then whenever a new variable comes per se, we would just keep it in between these two. And in that way, we are just increasing the pile, but always EVP is at the bottom and ESP is at the top. So what we do to destroy this track is basically we take that EVP, which is always in the base, to the ESP, and we just collapse the entire book pile. So we'll get more further into this later onwards, but this is the basic understanding of how a C program and an assembly code differs, but also how similar it is to each other. So next up, we have a concept called as ingenious. So what it basically means is that the bytes in the computer memory are read in a certain order. Just basically that's it. So before getting into the concept of ingenious as such, I would say, why do we use ingenious or this concept per se? Like, this is basically how the bytes are read in a certain order. So what's
We
something
want
new
you to
about
answer
it?
in the chat box. What do you think? Why do we use Indianness? Everyone. It's a simple question. I mean, it's a question to think actually, but yeah.
So I guess I should move forward because there are no answers regarding it. So see, this is somehow very simple concept, but the reason for this, it's not something that everybody thinks of. So exploitation basically means we think why a lot. So why do we use ingenious? How can I explain it? So there are different languages which is out there, right? So there's English, there's Malayalam, there's Hindi, there's Telugu. So in English, we read from left to right. But let's say Arabic, we read from right to left. So there's a difference in the way that we read, right? So this is exactly why ingenious is needed for computers also. If my computer reads the bytes from like left to right, and let's say your computer reads the bytes from the right to left, we're going to have issues, right? Because if you're not following the same order or format. So ingenious is basically a, a system, a format by which we are reading the bytes in a certain order. And there are two orders that we can read the bytes in a computer. So one is the big endian and the other is the little endian. So big endian basically refers to big end first. So when reading multiple bytes, the first byte or the lowest memory address is the biggest. So it makes the most sense to people who read left to right. So explaining further, we have big endian. So big endian is basically storing data starting from the most significant byte. And we have address. So let's say we have an address in the memory system, let's say 0x1000, 0x10,000, 1100. And you also have to store a particular value, which is 0x10203040. So how do we exactly store this? So in case of big endian, what happens is that we store the highest value. Let's say in case of big endian, the first byte of the binary representation of the multi-data type is stored first. So here, the first byte is being stored in the first memory block, and then 01, 0x20 is stored, 02, 0x30 is stored, and 03, 0x40 is stored. So in case of little endian, obviously, it's just completely opposite of it. So storing of data starting from the least significant byte. So we have the first same address, we have the same value, but in 0x1000, we have 0x40, then 01 may we have 0x30, 02 may we have 0x20, and 03 may 0x10. So this is the difference between big endian and the little endian. It is just an order in which bytes are read in a computer. And one important factor is that intelligence of a computer is specific to the particular architecture. So any doubts?
Yeah, ask your doubts, everyone. Why do we take 0, 10?
So basically, we're taking
Us.
a byte of it, and that is being stored in this particular address. So each byte of it is taken and stored in this particular addresses, adjacent addresses, which is over there.
Yeah, forget about 0x1 for 1000, everything. That are random addresses, that can be random addresses. Just to make it clear to you all, we are having that written down here. These are random addresses piled one above another. The first address, on the first address, 0x10 will be stored, which is the first byte. 0x10, 0x20 will be stored on the second address, 0x30 will be stored on the third address, 0x40 will be stored on the fourth address. Why 0x10 is taken and 0x20 is taken, not. Only we can store a byte in a specific address, right? We can't store everything. Ankit Chaudhary. Value is 10203040, but if you want to store a specific byte in a specific memory, then we'll have to take the byte itself, right? Any more doubts?
If there is any doubts, let's move to a small quiz set time.
Yeah.
Just a very, very simple quiz. We'll be giving you a form. You have to just fill out the answers. That's it. It's completely anonymous. You're not collecting any of your identity per se in email form or anything. So,
We'll put the link in a very short time. Yeah. We'll be answering the question, Ankit Chaudhary, after you all have given the quiz.
so if you guys have majority of you guys are done with the quiz time, let's move ahead.
That was the first answer. Are we still getting any responses? 14 responses we have got. The first answer is 0x40. Congratulations to everyone who has got it right. The second address, which is 0x2001 on the memory, will store 0x40 in big hidden format. Okay. The second question, which Linux command will change access permissions of the binary system objects? As I told you, it's going to be chmod. Okay. Chmod plus x and your binary name will access the permissions of the binary, will change the access permissions of the binary. Yeah. In the third question, the virtual memory, RXP indicates what? So this is a revision of your previous RE sessions. So R means read and X means executable. So you will have to mark both the options. Then when you get the point. And in the fourth, in assembly, which statement destroys the stack? The correct answer of this question would be leave. Okay. Leave, if you just search about it, leave means move EBP comma ESP and then pop EBP. So both the commands are situated into one. Then we'll get the leave command. Then you're done with the test. Yeah. So yeah, memory. So what is computer memory? So there are two types of memory in a computer. One is the physical memory and a virtual memory. The physical memory is the one we call RAM. You guys must be knowing. We have, someone has an 8 GB RAM, someone has a 16 GB RAM, and the virtual memory, it's the hard disk. We can relate it to hard disk. So why are RAMs not as big as hard disks? Because they're expensive. They are really fast in compared to hard disks. And yeah, so we don't have anything to do with RAMs as such in binary exploitation. We'll have virtual. We'll learn about virtual memory. So like every house on your street has an address. Each byte in the memory has a unique numerical address called the physical address. For the sake of simplicity or security, in the CPU in our computer creates a virtual memory of the physical address, which is paged, mapped, linked, anything you can say of the to the physical memory. Hence, the programs that we are gonna type are gonna be allocated into the virtual memory, which is the hard disk, rather than the physical memory, because physical memory is really small and we can't give them permanent allocations while typing some programs and all. So in the virtual memory, in the virtual memory segment, there are three types of permissions to us: a read permission, a write permission, and an executable permission. The read permission can read the data from the segment. The write permission can store or modify the data in the segment, and the executable permission can execute the machine code from there. So this is something which is really important to us: executable permission. Okay. Physical memory refers to the actual RAM of the system attached to the motherboard, but the virtual memory is a memory management technique. Using the physical memory, the CPU maps a virtual memory out of the physical memory, out of the RAM, and which allows the user to execute programs larger than the actual physical memory which is present. Which is actual physical memory means to be RAM. That's because that's why you have 8 GB RAMs in your devices, 8 GB, 16 GB, 4 GB, anything, but you have 1 TB hard disk and all. So that is why you can create a bigger map of the physical memory into a virtual memory, and you can store run lots of programs on it. Okay. Yeah. So anatomy of a program, and we'll be discussing the anatomy in the virtual memory, what happens in the virtual memory. So this is the basic program layout that we'll be discussing here. In the virtual memory, there are many segments. We'll start from the lowest segment, which is the text section. It contains the machine code of the compiled program, the code that we compiled after getting the binary, right? Then it has an initialized segment, This stores all the global variables that are declared in the program that we're going to compile, that we're going to make the binary of, and the constants that are initialized before the execution. We'll have a BSS section. It contains all the global variables and the static variables that are initialized to 0 or do not have any explicit initialization in the program. Then we'll have the heap section. And in this section, dynamic memory allocation takes place when some memory is needed to be allocated using malloc, calloc, etc. So malloc and calloc are C library functions. These functions, allocate data, allocate memory allocate memory during runtime when the program is running. Okay, and then there is a stack. It is the place where the function arguments, local variables, return addresses, and the processor state between function calls are stored at. So a stack grows from a higher address to a lower address, while the heap grows from the lower address to the higher address. The dynamic memory allocation takes place from a lower address to a higher address, and stack grows from a higher address to a lower address. We'll be learning more about it. Yeah. So what is a stack? So start imagining stack as a pile of books, like Aditya said. Imagine you have a table and the table is empty and just want to keep books on it. You keep one book, and on the one book you'll keep another book, and on the other book you'll keep another book. So there are 3 books already there. And there is a stack of books. Okay. Yeah. So why do we need stack in the first place, and what is a stack? In computer memory, stack is an abstract data structure. Okay, it follows the principle of LIFO, L-I-F-O, last in, first out, as seen in the picture. The last element which comes down at the stack, which is the element on the top, will go out the first. Okay, imagine the pile of books. If there's a box and you're piling up books inside a closed box, in a closed box with an open top, and the first book that you're going to take out is the last book that you're going to put in. Okay, try imagining like that. So we know that the code is made up of blocks called functions. Okay, so when you call a function, how is execution passed on it? How are arguments to the function, and how are arguments passed to the function, and how the function returns execution back to the function which it is called? The simple answer to all of these questions is stack. Okay, which is there in the memory. So stack has basically 2 instructions, push and pop. The push instruction, these are simple instructions which you can perform on the stack. Push makes space on the stack and moves a value on top of the stack. Imagining pushing a book on the top of the pile that you already have, that you're pushing a book, adding an item to the stack. Okay, and pop moves the element which is already there on the top of the stack out. It removes an item from the stack. So in case of x86 assembly, pushing a register onto the stack will subtract 4 from the ESP register. ESP is the stack pointer, okay, which you all have been learning since the last 2 days, and Aditya also told you. Hence, growing the stack upwards to make space, and moves the value inside the register on top of the stack. So if we are pushing EBX, then EBX will be on top of the stack. Okay. Similarly, there's a pop EBX. If there is a pop EBX, though the pop EBX will move the value on the top of the stack to the EBX thing. Okay, to the EBX register, and destroy the space that was allocated for it. Okay. If you have any doubts, please feel free to ask your doubts on the chat box. We'll try to answer. So, yeah, stack, as I said, grows from a higher memory to a lower memory, and 2 instructions that keep track of the stack are ESP and EBP. So, as I said, imagine a table with a pile of books, 4 books. The 4th book will point to the ESP. I mean, the top of the stack is the 4th book, right? You can imagine a table with 4 books, a table with 4 books. The 4th book is the topmost book, right? It will point, the ESP will point at the 4th book, and the base pointer is the first book that you put. Can you understand? Similarly, in memory happens like that. The base pointer points to the bottommost of the stack, and the ESP points to the topmost of the stack. Okay. So there's function prologue and epilogue. So this is something really technical. The stack frame of a function is a section of stack which is used to allocate variables and pass parameters and functions. Used to pass parameters. So function which makes a call to another caller function, and a function being called is the callee function, right? So when the function is called, the return address of the return address is pushed onto the stack, and then a new stack frame is created. So how a stack frame is created in the memory? When a function is called, the return address is pushed onto the stack, and then a new stack frame is created. Okay, listen to me carefully. So how a stack is created in memory? You all know about registers, right? EBP, ESP. Okay, these two are registers that is required to create a stack or destroy a stack. So what is EBP? The EBP is a base pointer of the stack, as I said. The register that points to the lowest, that the bottommost table, that points to the table. Imagine that. Okay, it points to the table. Then, when there is no books on the table, and you are trying to imagine a stack when there are no books on the table, there is no stack. So the base pointer, the base and the top of the stack, the base of the stack and the top of the stack are same, right? So we are moving ESP, the stack pointer, the ESP which points at the top of the stack, to EBP, meaning the stack is really empty now. There are no books on the table. There are no elements in the memory. Then we are subtracting some number from ESP to create some space for the program for the program code to execute. Yeah. Then that everything, the execution inside the program, now the stack is created, everything inside the program occurs, everything happens, and now we are reaching how we are now we'll be telling you how we are going to destroy the stack. So there is a leave function that had that was there on the quiz. The leave function means move ESP to EBP. Okay, I'm sorry, move EBP to ESP. So the base pointer is now equivalent to the stack pointer, which is already there before. The stack gets destroyed like that. Now you're just moving the ESP, which is on the top of the stack, to the EBP. Stack gets destroyed after that. Okay.
So now we decide on the fact that we know what a stack is, but what we have to do right now is why is a stack born? How is a stack born, and what we use stack generally for? So whenever a function is called, the stack frame for that function is pushed into the program stack. Various elements in that stack frame is the RIP, save registers, local variables, etc. So just say that you have two functions, int function 1 and int function 2. And there's another function, int function 3. So inside the int function 1, int function 2 is called, and inside the int function 2, int function 3 is called. So what happens is that, imagine a huge pile of books together being pushed onto the table first. So when function 1 is being called, so what happens is that a function is called. So like I said before, when a function is called, a stack for that particular function is being created. And if that particular function has any sort of variables that is being pushed to the stack, and also if any parameters of that particular function which is going to be called is also there, that is also being pushed into that particular stack. So let me explain you further with a diagram. So this is basically a stack frame of a function. So let's say there's a function f1 or a function 1. So there will be EIP. So EIP is basically the return address of the previous function as such, or the calling function. So next is the EBP. So whenever you create a stack, the first thing you need a base to the stack. So the first book that is to be kept on top of the table is the EBP. Okay. So in this function, if we had any sort of variables per se, say int a is there, so that variable int a is equal to 0 is there. So that the value 0 is being pushed into the stack. So that will be over here in the local variable sections. So how many more variables we have that will be pushed into the stack? So we'll want as many variables as there it is. Then after that is the parameters. So let's say that you have a function, let's say function 2 is there. So where you need parameters to call the functions. So when that is there, all the parameters have also been stored in the stack. So right now we're talking about the 32 byte. So in 32 byte, this is the way how it works. So one important thing is that EIP per se is, imagine you're going to a new restaurant, but you basically don't have a clue on like an idea of how to reach there because it's like extremely new and it's extremely far away from your house. So you reach a junction till where you have a very good idea of how to move around. But after the junction, you have really no clue how to go forward to that particular restaurant. So that junction, like from where you know how to go to your home, or the junction which is like the pointer, is EIP. And the far off place which you have no idea, or the restaurant that you're going to, consider that as the next function. Okay, for time being, get this idea in your head. So like I said before, you have function 1, function 2, and function 3, and these are stacked on top of each other. Okay, so a stacking on top of each other will also be done on a like a broader perspective on this way. So this can be said as a function 1, and this can be said as function 2. And this particular EIP is basically the return address or the address of this particular function. So let's say that we are going from one particular okay, we are going from a home to a particular restaurant. Okay, the restaurant is a function 2. So we are in function 1, which is our house. So we are going, but we reach a junction where we know how to go from function 1, starting of function 1 to this junction. But we have not too much of clue to how to go to function 2. So we just, make sure that this particular junction is there in our radar. Like even if we get lost, we know how to come back to a home through this particular junction. So EIP is basically that, a junction from where you can go back to the function that is calling you. Okay. And now I'll explain what stack frame is. Stack frame of a function is basically a section of a stack which is used to allocate variables and pass parameters. So that's basically the entire ordeal which we have been saying for the last 5 minutes. So any doubt regarding this, please type down. We would be clearing it.
We'll be also checking the InCTFj server, and you can ask it downstairs if you're shy to ask me on YouTube. We'll wait for 2 minutes and then. No, no.
So if there's no doubts, let's move ahead.
Yeah. So we'll jump into exploitation, jumping into the cool stuff now. Now where we will learn how to look into the stack from an attacker's perspective. Okay. And again. So as Aditya said, we have an EIP control, the instruction pointer. Instruction pointer points to the return return address. Okay, the return address, what if we can have that control of the return address? What if we can control the place to where we can jump? Say we have a control to write data anywhere on the stack. How can we exploit it? Why is the stack a common attack vector? These are the questions that must be coming on your mind. So in the last section, in the previous sections, we've been learning that when a function wants to return execution control back to the caller function, it performs the function prolog, in which the final value is the address to the next instruction to be executed. Okay, it performs a function prolog in which the final value is the address of the next instruction to be executed. So what if we control that? The EIP has the value to be executed to the corresponding count. So it means that we can get a function to return to any memory segment which has executable permissions. Remember, R, X, and W read, executable, and write permissions. If a memory segment has executable permissions, you can return to that part of the memory segment, and you can execute whatever you want to do, only if it has an executable permission, which is important. But in practice, we don't have access to any addresses on the stack. That is something different. But for now, we have to exploit some vulnerabilities in order to attack the stack. So let's discuss about some stack attacks next. So the stack-based attacks are buffer overflow, which is popularly known as buff, red to win, red to shellcode. You'll know what a shellcode is. ROP. ROP means return-oriented programming, and there's a red to libc. Okay, so we'll be learning about buffer overflow. We'll not be learning about buffer overflow today. We'll just giving you an idea about buffer overflow, and that's for you guys to think about it. How we can exploit a real buffer overflow challenge. That's going to be a task for the next. Come on. Quiz time. Someone was excited for the quiz. I don't know. So.
We will be giving the link of the quiz in the chats. So please
Chats.
go ahead and answer.
Okay. Okay, there is no quiz link on the chat box.
Okay. The link of the quiz is given.
Sandeep Kumar Sharma, shout out to you. Good. If you got 4 out of 4 and 5 out of 5. Static memory RAM.
I think sufficient time has been given to like answer the quiz. I think we should move ahead with the next topic.
Should we discuss the quiz or should we move? Let's discuss. Okay. So what is a stack pointer? Everyone, I have seen that the responses for what is a stack pointer, only 16 people have got it correct out of 22 responses. That's nice. ESP is the stack pointer. Good. The next question is, what are the stack based attacks? Yeah, the correct answer is everything. Buffer overflow, red to win, red to shellcode, return oriented programming, red to libc, and all. Okay. Parameters to a function is passed through stack in 32 bits, but in 64-bit it is stored in registers. Into dash registers. Okay, 6 registers. That's the correct answer. Okay. Stack is LIFO. We have told that. People should not be getting this wrong. Okay. Yeah, yet 2 people are wrong here. Anyways, it's fine. Completely fine. Last in, first out. Stack is last in, first out. Which type of memory cannot access the CPU? The correct answer is virtual memory, and the people who have put a dot, question mark. People who have put virtual RAM, virtual memory, external memory. Yeah. Some people are correct, some people are wrong. Okay. People who had the idea that something virtual, then you can consider yourself that you have got a point. Come on. Okay. Let's continue. So I'll be explaining what a buffer overflow is. Okay. So coming to buffer overflow, you've been hearing about it. What a buffer overflow is, what are the stack-based attacks, BOF and all. So first we'll learn what is a buffer specifically. Okay. So a buffer is an area of memory set aside to hold data temporarily. Okay. Buffer is an area of memory set aside to hold data temporarily while it is being transferred from one location to the another, or even to another program itself. So the buffers are set up in every program to hold some data coming in and out. For example, you must be streaming, must be watching some videos in YouTube, right? You'll be seeing that the video has already been loaded. Some for some part, and the program uses buffer to store the advanced supply of the video data to compensate the delays, that so that you don't face any delays while watching the video. So we'll see how these buffers work in a normal C language, normal C program. Okay, so next slide. Imagine there's a variable char buffer and it stores a value of 20 bytes. So as an attacker, as a person who wants to hack, who wants to exploit a program, a computer, target computer, and if you see this, that it stores a value of 20 bytes, what all things can you do to make it to manipulate it? I want you all to answer it in the chat box. What do you think that you can do to this? What can you put on the variable buffer so that it can manipulate it? Please write that. Please write your ideas on the chat box. Okay. I'll be giving you 1 minute. Write your ideas. Since I can't see any answers, so yeah. So as an attacker, someone would try to overflow it. Someone would, it stores 20 bytes. I'm thinking, what can be done to this? What if I give 21 bytes to it? What will happen in the memory? Okay, the buffer is stored into the memory, right? What can we do to the buffer? If it's storing 20 bytes, then what can we do? We can obviously give something greater than 20 bytes. We can give 21 bytes, 24 bytes, 28 bytes, 38 bytes, 50 bytes, as long as we want. So a buffer overflow, as the name suggests, it occurs when the volume of data exceeds the storage capacity of the memory buffer. Okay, memory buffer, on the last slide we got it as 20 was the memory buffer. Okay, what if we try to input 40 bytes in that 20 memory buffer? So as a result, the program attempting to write the buffer overrides the adjacent memory locations. A buffer, the buffer variable is stored into the memory segment, right? So if we overflow the segment with a volume that exceeds the storage capacity, it will obviously override the addresses above it. Okay, so consider an example. You have a program, okay, that asks you to enter a password credentials which are 20 bytes long, as the buffer which was mentioned on the previous slide. And however, for some reason, any vulnerability, which is going to be there on the program, for some reason you are able to enter more than 20 bytes. So upon doing so, you see that your program crashes with a secfault. Okay, but why does this happen? Okay, by definition, what is a secfault? Secfault, if you will just elongate it, a segmentation fault, often shortened as secfault, is a special kind of error, which is caused by accessing the memory that doesn't belong to you. You're having 20 bytes as a buffer. If you're giving 40 A's as your password, it will obviously write the adjacent memory. It will write the memory which is just above it. Okay, so it will change the memory. So when the return address, when the EIP points to the return address and the memory is overwritten there, the computer won't be understanding where to return to. Okay, for easier way to understand this, whenever program does not understand where to return after the execution of a certain piece of code, it crashes, causing a memory access violation. So when we receive a secfault, because the program has allocated only 20 bytes of space to your input buffer present on the stack. Due to the flexibility to enter as many characters as possible, you can enter, if only 20 bytes is allocated, right? But you can enter any bytes, any number of bytes, as many bytes as possible. You enter a string of characters having length greater than 20. As a result, the adjacent memory locations on the stack also gets overwritten by your input. So when a return pointer on the stack also gets overwritten due to the same effect, the program doesn't understand where to go next. The return pointer is corrupted, is overwritten by you, just because you entered 40 bytes when you're supposed to enter 20 bytes, now the return value is overwritten. So the program won't understand where to go next. So hence the secfault will come. Okay. Next thing.
So to basically going to show you like what exactly we have been telling about the sec fault, and also like how we can give more input than what it asks for, and all those things through this one particular program. So just consider this program as a simple C code where you have this main function inside which the auth has been initialized to 0, and there's a character array of 20 bytes, and then there's a printf statement, and then there's a gets, okay, and gets of the particular array as such. And then we have the if condition, and it basically says that if the auth is is not 0, then we will get the access granted message, and else if the auth is 0, then we would get the access denied message. So as an exploiter's perspective, what I want is the access granted message. So what I'm supposed to do when I see this particular program is how can I make the auth, the value of the auth, to be 1 and not 0. So when you think about it, it's pretty much possible if I could just simply change the int auth is equal to 0 to int auth equal to 1. It's done and over and a go. So, but what if this particular program is in your system and I want to change it while I'm working in my system? Like, let's say that we have an NC connection between each other where I could just simply give any sort of input, and the program will run based on that input in your system. Okay. So in that case, I don't have access to the source code which is there. So I need to change the input. I need to change the value of the auth based on what I give as an input. Okay. So it's quite hard to understand, but stick with me through this. So first of all, let's analyze the code per se once again. You have a main function inside which auth is being initialized to 0. Okay. There is a character passphrase which is of 20 bytes, and then there is a printf statement, and then there's a gets of the passphrase as such. So you're inputting passphrase, and out of which 20 bytes are all that we can input according to what is being declared. And then there's an if condition which says that if auth is equal to 1, you get the access granted message, or if auth is equal to any values except for 0, you get that access granted message, but if not, you get the access denied message. So if you just simply run this particular code, what do you get? You will get the access denied message because in this code, auth is equal to 0. But what we are trying to do is that we are trying to change the value of the auth to something else, to some other value, so that we could get the message access granted. So this is basically the essence of exploitation per se, as simply as I can say, to alter the given source code, but by not just simply just going and just doing delete and just putting 1 instead of 0, but it all depends on what we give as the input, because that's the only way that I have any control over this particular execution of the program. Let's say that this program is being executed in another computer. The anything that I can do is simply give an input. So I need to give an input in such a way that it overrides the value of auth to 1. For time being, let's make it to 1. You have to override the auth value to 1. So when you think about it, override the auth value to 1. So we should give an input, right? So nobody is asking me auth, nobody's asking me gets auth. So the value of auth is not being changed at all. So the only thing that I can do is to give the value of passphrase as such for 20 bytes. So basically, when you think normally, we are just giving the value 20 bytes, we're just giving it to passphrase as such. See, what's so wrong with it? See, the wrong or the problem with this particular code is what we have to find. Like, the vulnerability of that particular code. Like what makes it vulnerable enough that even this is a simple program where we should just give a cat passphrase of the 20 bytes, we just give a 20 bytes ka input and the program should give us access denied. Why does it like, how can we just change the odds value? So in this particular program or generally also, there are certain functions in C which is by default kind of considered to be dangerous or faulty per se. So in programs or the initial levels when we're doing binary exploitation, we are supposed to find that faulty functions. So in this code, when you see like int main, it's a normal one, int auth, there's nothing faulty regarding it. Char phase, there's nothing faulty. It's simple if condition. You can't do nothing about it. But the only time it calls in another function per se, it gets. Printf, there isn't. I mean, printf generally has a one, but in this particular case, it doesn't. So the only place we would be looking more into is the gets. See, like gets is the only way we could just give an input to this particular program. So let's look further into gets per se. So we have gets. Gets is this one particular function where, uh, you know,
It
when
takes
you
no limit
compile,
of the number of characters
yeah,
to be read.
when you compile a normal C program using GCC, like GCC minus O hello.c, you could see a warning coming if you're using a gets. That gets is very dangerous and we're not supposed to use it. So if after the session is over or even right now, just compile a normal hello program just using prints and using gets, okay? And just simply compile it, you'll get this warning. So why is this warning there? So warning is there is because gets is considered to be very dangerous. And the reason is that gets is basically is just taking our input, right? So the main problem with gets function is that there is no limit to the amount of input we can give in a gets function. So let's say the limit here being mentioned is 20, right? So what happens if I give 21? It's absolutely fine for gets. If I give 22, gets is fine with it. If I give 23, gets is fine with it. Even if I get almost like 20, I don't know, 40, gets is fine with it. Gets is absolutely fine with the value that we give. Because in gets, the gets continue to read your input, until it encounters a new line or terminating new line character. So if it encounters a terminating new line character, it replaces it with a null byte. So this is an obvious vulnerability. So imagine there is this program running and I can give as many input as I want. So what happens if I give as many inputs as I want? Because I showed you before this is basically a stack frame, right? I showed you the stack frame. So we've seen that local variables are like stored like one above the other in like a stack frame, just like in a stack. Imagine a table and the local variables are just stored one over the other, bang on one over the other. So what happens, and for each particular local variable, there is a specific defined set of space allocated for. In this specific one, the 20 bytes of space is allocated for it for definitely. So what if I give 21? What would happen? Stack space is already allocated. So imagine there is this cup of water and the cup is just 10 ml. And then for 5 ml, I'm filling with water. So what if I put a 6 ml? What happens? It just fills more, right? So it just takes up more space. What if I fill it with 7 ml? It takes up more space. So what happens is, imagine the same thing, a glass filling up. But what happens is that each and every single ml has a specific address. Okay. So this auth value will be stored. Like, I'll just give you a explanation. So imagine, so this is basically you have a particular character passphrase and just 20 bytes. So 20 bytes, all that it can store is still here. But our int auth is over here. Okay, and it is 000 as mentioned here. So I should do something in order to be keeping on writing it over here. I kept on writing it over here, all the addresses, and then I need to overfill it in such a way that I change the auth value to something else other than 0. So that is basically what buffer overflow generally is. So you just have to change whatever value that you are giving and make that particular value change any particular variable over here. So what, according to buffer overflows, like there are different ways we could do buffer overflows. We can just override the RIP and just take the control of the RIP and give it to a particular function. Or what we are doing here particularly is that we are taking the input per se and we're using it in order to override the adjacent memory space. And if there's a local variable in that particular memory space, then we are overwriting the value of that particular variable. And that basically is buffer overflow. It's basically the buffers commonly hold a user input, and mistakes when writing to them could result in like attacker control data. Like whatever input that I give, that will be pushed onto any of the local variables which is there in the stack. So this is how it is. So just think of how do you do it? How do you think that we will be able to do it? So the vulnerability of the particular program that we showed you is the gets passphrase, which is basically gets takes no limit on the number of the characters to be read. So we got the vulnerability. We know what to change. So what should we do right now? We have to change the auth value so that we can get the access granted message. We know that our input is being taken into this particular char pathway. So whatever value as we give here is the only way we can input value into this particular program. So how can we use this in order to change the value of auth? So think about it. What are we supposed to do?
And type it on the chat box of your ideas. Obviously, you're welcome to it. And tell us, how do we exploit a simple buffer overflow challenge? What ideas do you guys have as beginners? We will be explaining it to you, obviously. Prabhat Pandey gets
to be explained once again.
Gets to be explained again. Okay.
Gets is okay. Gets value. So you have gets passphrase, right? So passphrase is this particular local variable that we have defined, okay, which takes 20 bytes as an input. So it should only take 20 bytes as the input. But what gets does is that gets is a function where we can give as many input as possible, and it would just keep on, taking it. It would not, it would not stop. Like if you're using scanf per se, or if you're using fgets, what happens is that yes, it just takes the amount that it's supposed to take. But the problem with gets is that it only terminates, or it only it only stops taking our input when it reaches a new line character. So until then, it just keeps on taking whatever that we are giving. So let's say right now we're only supposed to put 20 byte, right? I can put 21, I can put 22, I can put 23, I can put whatever number I want, and the program just keeps on taking it. It won't stop taking it. So like if you want, I'll just run the code and I'll show you how to do it. Can you guys see my terminal per se? Can somebody confirm whether you guys can see my terminal?
No, we can't.
Okay, 1 second. Can you see my terminal?
Yeah. Now I can see it.
So, okay. So this is basically, we have this particular program that we showed you earlier, and we are going to run that program in GDB. See, this is what you saw, but basically in a more of a binary form that you're seeing right now. So this is the program that you saw, and this is the binary file that I'm running in GDB. So let's say I run it. So it asked me to enter a passphrase, right? So that was basically our program also. It just asked me to enter the passphrase. So let me just 1 second. So see, you can just see the code side by side while I'm explaining. So over here, you can see the code, right? So you have to get of the passphrase. So you have to get passphrases there. So they're asking for the passphrase. So that's exactly what is happening here also. It's asking for the passphrase. And basically it said that we can only give 20 bytes. Okay. So 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 20. So it's 20 ones that we are given. It just showed access is denied. Yes, because we didn't not exactly like, okay, access is denied. Let's get to buffer overflow later. Just gets explaining the gets function. Okay. So we are given 20 inputs right now, and the gets was happy. Gets was fine with it. So let's say we give more than 20 input. This is what happens. The program does not like, it just keeps on taking it. The gets function's problem is that it just keeps on taking it. It does not exactly terminate until and unless it encounters a new line. So you can just give more than you're supposed to give as the input. And that's exactly is the problem with the gets. So did you understand the specific person who
We have an access granted also. You can see that access granted.
so you can just think about how we got the access granted.
We have changed the value in the auth variable, and we have passed the if function which was there, and we have access granted. So successfully we have exploited this program. But to write an exploit in an official on an official server, in a server of a target computer, we require a lot of new things, a lot of stuff for you to learn, and that will be covered tomorrow. Okay.
Yeah. So right now what we did is that we gave an input, and that we showed you two things. Okay. So over here we could see that when we first gave like around 20 bytes of one, we gave that access is denied. Okay. But when we give more than 20 bytes, we show that access is granted. So what exactly do you think has happened that made it show access is granted? What exactly happened that made the auth equal to a value which is not 0, and that gave us access granted? So that's exactly something you have to think.
Changed it. Akash, there is no obviously there is a way to find the exact number of characters, but for now just understand that we are just overwriting the value which is there in the auth, which is 0, to something with our input. Okay, we are giving a number of ones greater than 20. Okay. So we'll be overwriting the address, overwriting the value which is already stored in the stack for auth, which is 0x0000, 8 zeros, and yeah, we'll be overwriting it. So it won't be 0 anymore once we overwrite. Once we pass 40, 50, 60, how many number of ones that we want, because it has a getS vulnerability, we'll be overwriting the auth value of auth in the stack. So once it gets overwritten, the if function, if auth is auth is not equal to 0, so yeah, it is not equal to 0, then access will be granted if it gets overwritten.
Can you mention some of the details of this exploit? Like what if my input overrides an important value or something? So important value. So we want it to overwrite a particular local variable over here. So if you're asking about important value, I think you might be referring to canary per se, but right now it's canary disabled. Or if you're not asking for that, okay, completely forget about what I'm telling. But if you are intended to canary, see, we are not specifically speaking about that over here, because Kind of
Like
a little bit more.
base pointer. Okay. It will crash, I suppose. Now, just because it has getters vulnerability, right? You know, you have a passphrase. Ankit Chaudhary, I'm talking to you. You have a passphrase which has 20 as its memory value. We can only write 20 bytes on it. But what if we write 40 bytes using the vulnerability here, which is getters? Okay, we will be overwriting what is there on above the stack. If there are, you can see the diagram, right? There are 0x4018. Till there we have the memory for the passphrase. But what if we give 40 bytes? It will obviously write the memory which is above it, and it will somehow reach the memory where auth is pointing, right? 0x00, and it will overwrite that. Simply the auth won't be 0 anymore once it gets overwritten. So since it's not 0 anymore, if function will become true, and printf will and the program will print access granted. Okay. Is the doubt clear, Ankit? Yeah, I guess it should be clear. Anyways, if you guys have any more doubts, please ask us. This is the time. There are there should be questions. So,
Auth here is basically it's just a local variable. Like int a is equal to 0, the same thing. In there, int a is the variable name. So auth is just a variable name which is used over here.
yeah. Okay. Any more questions? We'll be there for 5 minutes or 2 minutes. Okay. Please feel free to ask us, and we'll have a session tomorrow. We'll be showing how to write an exploit, how to write an easy exploit of a simple buffer overflow tomorrow, and some more stuff. No, we won't be doing any Tragoda challenges today. I guess there are no questions. They're all enjoying having a good time. Okay. Where did you get this? We can wind it up, Aditya. Thank you, everyone. Thank you very much. Okay.
Thank you all for attending the session.
Attending the session.
Where did I get the name from? Google. Introduce you as your friend.
Can you guys go to the sponsors slide just once more? Yeah, so we'll be concluding today's session, and tomorrow will be the last session of the trainings as part of InCTFj 2021 and InCTF Nationals 2021. So we would like to again thank our sponsors for making this event possible. And yeah, I would like to thank our event sponsors, Salesforce, our diamond sponsor, Zoho and VMware, our platinum sponsor, CrowdStrike, and our gold sponsor, Cred. And we have two silver sponsors, Gyana Varga Technologies and H&R Block. So we would like to deep-heartedly thank all these sponsors. Thank you.